Presentation title is the recent progress in rare earth ion activating molybdate-based phosphor for versatile applications. My name is Jesse Yu, professor in Kyunghee University. Contents include introduction, preparation, progress, optical thermometers, molybdate-based phosphor for white LED device, and the field emission display application. After that, I'll summarize. Phosphors are solid substance. This illustrates the luminescent phenomena in these pictures. Rare earth ions include 15 kinds from the lanthanum to the lutetium. In this group, with the characteristic intra-configurational of POF transition in these periodic tables. This slide shows the principle of luminescent material. Phosphor is composed of host lattice and activators using rare earth ions. For down conversion, host material absorbs the lambda-1 activator provides the excitation. After relaxation, it emits lambda-2. In this case, lambda-1 is larger than lambda-2. For up conversion, host material absorbs S1, excitation 1 by sensitized, excitation 2 by activators. After relaxation, it emits lambda-2. In this case, lambda-1 is less than lambda-2. This table shows the characteristic, the emission color for the rare earth ions. Each ion, the response to the emission, the transition, related to the emission wavelengths. The host material influence on the luminescent property of rare earth ion activated phosphor include the double vanadate material with strong absorption and broadband luminescent region, and the fluoride material with low phonon energy and stable structure. It has many advantages of high luminous efficiency, the long service time, the eco-friendly features, and the stable structure. This molybdate-based phosphors provide novel structural relation property of low temperature synthesis and the high economic value consisting of a charge transfer band from the ligand to each transition metal ions. This phosphor can be used for different applications, including the white LED, the flexible, the display film, and the optical thermometers. This slide shows the preparation, the process for phosphors. From this picture, initially the raw materials are mixed manually in solid state method or the uniformly dissolved in an aqueous solution in sol gel and hydrothermal method. The reaction is performed at elevated temperature. After that, is calcined at the higher temperature to obtain the pure phase form. Then the obtained phosphor material can be used for different applications. This one details for synthesis of material and structures. Solid state method, sol-gel method, co-precipitation method, and hydrothermal method. This solid state method requires the high temperature. The control of the size of particle is difficult. In contrast, using the hydrothermal method, it provides easy and precise control of the size, shape distribution, and crystallinity. Optical thermometers, principle and motivation. Conventional thermometers are based on the principle of the liquid and the metal expansion. Also, it has many disadvantages, including long response time, the contact measurement, and limited operating environment. In contrast, non-contact optical thermometry is based on the temperature-dependent luminescent emission spectra of rare earth ions using phosphor material. It use the fluorescent intensity ratio, the FIR technique. Also, it has the real-time monitoring, the fast response, high sensitivity, and the high spatial resolution. These equations, for the FIR value, the absolute sensitivity value, and the relative sensitivity, the value. Using these equation, we can obtain this kind of value. This one shows the up-conversion optical thermometers. The gadolinium, the molybdate, the phosphors. By changing the erbium concentration from 0.323 mole% in green emission region, at different temperature, the 300, 390, 460 Kelvin. The FIR value can be determined based on the FIR technique. In this case, maximum sensitivity 10.57, the 10 to the minus 3 per Kelvin at 450 Kelvin. The erbium concentration, the 0.3, the mole%. Increasing the erbium mole concentration, then the maximum sensitivity is decreased due to the increased energy transfer via cross relaxation. So doping concentration strongly affects its sensing sensitivity. This one shows the down conversion optical thermometers. The sodium, the tantalum, the molybdate. Here the diphrosium is the dopant. With increasing the temperature, FIR value is increased due to the different response time of the diphrosium transition. This absolute sensing sensitivity is obtained at 700 Kelvin. Sensing property depends on the doping concentration. From the heating, cooling, the cycling measurement, it confirms the stable sensing performance. This view graph shows the optical thermometer performance in recent molybdate-based phosphors. This one shows the up conversion. This one shows the down conversion. This one shows the absolute sensing sensitivity value. The second application is white LED devices. The phosphor converted white LED. This one is the third generation lighting source based on the UV and blue LED instead of the incandescent and the fluorescent lamp. It has many advantages of the high rendering index, the long lifetime, the high efficiency, 50% electricity savings. For the fabrication of the white LED, there are two methods. The first one, the indium gallium nitride-based blue chip using the yellow-emitting phosphor, the YAG-cerium. It provides a low color rendering index less than the 80, high color temperature larger than the 7,000 Kelvin due to the lack of lead-emitting phosphor. The other one, the NUV, the ultraviolet, the chip to excite three color, the phosphors, red, green, and blue, which provides a high CRI value. This one shows the molybdate-based phosphor for the white LED device. The calcium, gadolinium, molybdate, phosphor, the CIE, the chromatic coordinate is here. It is close to the commercial lead emitting the phosphor. Then it's using this lead component packaged LED provide dazzling white light with high CRI value, the 82.6. Also, the CIE chromatic coordinate is this one, the white region. This one shows the molybdate-based phosphor for white LED device. The emitting region, the green, the red, using the near UV, the chip. Then the CRI value is obtained above the 90. This one shows the field emission display application, the using molybdate-based phosphor. This FED is consisting of phosphor anodes and the field emitter array. The outstanding advantage is the low energy consumption, fast response time, the wide view angle. This sulfide phosphor type the phosphor, such as this kind of material are popular and recognized for possible FED phosphor. It provides high efficiency, but this sulfide host is easily resolved and release sulfide gases under the electron beam bombardment. It is resulting in the loss of the luminous efficiency and the stability. So we should develop a novel, good host material with excellent the chemical and physical durability. This one, the calcium, the molybdate, the phosphor, the field emission display application, doping of the sodium, the potassium ions in this host material, the phosphor, the Cl emission intensity is increased with the increasing the operating filament current and voltage. So also the electron, the penetration depths in Cl can be estimated by the following equation. This is a summary. From this result, this molybdate-based phosphor material are very promising. Also can be used in different applications. Will be applied in the novel application in the near future. Thank you for your attention.